This is MG5004 Topic 4 Class 1. This is the video that replaces the one with no sound. So MG5004 DE5418 Topic 4 Class 1. This is MG5004 DE5418 Topic 4 Class 1. This is to replace the video that I made last week with no sound. So this one has sound. An exponential function is any function that contains a power. A more common type of function that we talk about is the exponential function, and these functions contain e. E is a constant, e is a number, and e is approximately 2.7183. And you can either find that on your calculator as e to the power of 1, or you can take it from the original, which is how it was worked out. Plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus, because this term here is actually 1 over 1 factorial. The same rules for ordinary powers apply to this special sort of exponent as well. So we can add the powers when we're multiplying. And sometimes it's quite common to just replace the e to the power of c with some number, some constant itself, because e to the power of a constant will be a constant. Similarly for division, and again with multiplication, we could rewrite that as that, and we could say where a is e to the power of k, then e to the power of kx is equal to a to the power of x, or capital A to the power of x, whatever. So we can do things, we can use our calculators, we can do things like 5.6823 divided by e to the power of negative 2.1347. That's just a straight calculator job, which would be approximately equal to 48.0416. Now let's have a look at something like this, because we need to look at these later. E to the power of 2x plus e to the power of x over e to the power of x minus 1. Now, if we factorize the top line, so we've got e to the power of x times e to the power of x, because e to the power of x times e to the power of x is e to the 2x, plus 1 divided by the e to the power of x minus the 1. Then we can cancel out these e to the x's, and we have e to the x plus 1 minus 1, which is equal to e to the x. Exponential functions have graphs that are called growth curves, and this is because when a number is multiplied by the same number, it grows, would you believe, exponentially. So just on that line there, if we've got y equals e to the 1, then y equals e to the 2 is e to the 1 times e to the 1. So it's growing pretty quickly. When x equals 0, then y is equal to e to the power of 0, which is 1. So a basic y equals e to the kx curve is going to pass through zero, 1. So if we were to draw that, like that, it would look like that. If we were to draw e to the negative x, it would be the other way. and it too would go through the point 0, 1. The key features of an exponential graph are that the greater the base number, the steeper the curve. So y equals 3 to the power of x is steeper than y equals 2 to the power of x, for example. The larger the value of k, so the larger the value of k in y equals e to the kx, then the steeper the curve. Now, let's have a look at, say, y equals b e to the kx. Then this time, what are we going to have? If we have x equals 0, then y is going to be b times e to the 0, which is b. So in this case, it's not going to go through 1, it's going to go through b. Before we sketch this one, just make one important distinction here. It says that x equals 3 plus 2 e to the negative t. That's because we're going to put t on the horizontal and x on the vertical. Now, this pattern's going to be the same. The way we do these is going to be the same for all types of graphs. When t equals 0, then x is equal to 3 plus 2 e to the 0, and that's going to be 2 e to the 0 is going to be 2, so it would be 3 plus 2, which is 5. So the vertical intercept is going to be 5. Now what we need to look at is, as t is getting bigger, so as t is tending towards positive infinity, t is getting larger, then x gets closer and closer to 3 plus a tiny number, since the bit that we're adding on, 2e to the negative t, gets smaller and smaller and smaller. So we're adding on a very, very, very small bit. So we're getting closer and closer to 3 from above. That's how we write that. Let's have a look at, we're going the other way. As t is tending towards negative infinity, so t is getting really small, then x is going to be equal to 3 plus 2e. Now, we can't really have negative infinity, but if we try a few numbers, if we try really large negative numbers, then of course the power becomes positive. So what happens is that this whole thing tends towards infinity, because this bit tends towards infinity, gets bigger and bigger. Right, let's put those two bits together. As the graph, as t goes bigger and bigger and bigger, so as we move out to the right hand side, the graph gets closer and closer to 3. From above. So that means that somehow the graph is coming in like that. Like that. It's not hitting the line, but it's coming in closer. It's got to go through 5, and then on the other side, as t gets more negative, the curve flicks up to being towards positive infinity. So it's going to come in like this. Oops, without the bump. Like that. it has what we call an asymptote at y equals 3. So putting all that together, the graph is going to go through 2 and it's going to go up towards 4 from below. It's not going to cross that line. Mine looks a bit close to crossing it. Now thinking about this, if t is time, then we're not actually going to have anything to the left of the vertical axis. So our graph is indeed going to start on the axis. We'll do this third one in class. The hyperbolic functions are analogous to trig functions, but instead of being generated by a circle, they're generated by e to the x. So we have sinh x, S-I-N-H x, hyperbolic sine, pronounced cinch or shine. We have hyperbolic cosine, which is pronounced sensibly enough, cosh. We talk about hyperbolic tangent, and that rhymes with branch, so tanch of x. And then we have the same for the hyperbolic cosecants, the hyperbolic secants, and the hyperbolic tans. And you'll notice that they're all coming from some sort of combination of e to the power of x. Hyperbolic functions have particular applications to engineering and to science, and often you express the equation of a catenary. That's where you've got something, say a suspension bridge, you've got two poles and the cable loops down between them. Often that is modelled on this kind of hyperbolic function. As usual, and as you would expect, there are rules governing the behaviour of cinch and cosh, and there are just some of them as well. And we can use these to prove various identities. For example, let's prove that hyperbolic cotangent squared of something -1 is equal to hyperbolic cosecant squared. Let's look at the left-hand side. Now, any type of cotangent, whether it's hyperbolic or circular, is going to be cos over sine. So this one will be cosh squared over cinch squared -1. And if we put that over a common denominator of cinch squared, now, have a look at the identity number 3, so that now you'll see that the top line is equal to 1. And our left-hand side now, by definition, is equal to hyperbolic cosecant squared. And you can prove all sorts of things using those identities. This is where we start to use hyperbolic functions. Just to remind yourselves, e to the alpha z is going to be, from the previous page, like that. And similarly, e to the negative alpha z would be cosh minus cinch, like that. So those are just by definition. Now, if we're trying to express the voltage V equals etc., etc., all we have to do is replace the various powers by whatever they are. So V is going to be 7 times cosh alpha z minus sinh alpha z plus 3 times cosh alpha z, plus sinh alpha z. And all we've got to do then is collect up the like terms. We've got 7 cosh, 7 cosh plus 3 cosh, so that's 10 cosh alpha z, and we've got negative 7 sinh plus 3, so it must be minus 4 sinh alpha z. The analogy between circular and hyperbolic functions, the circle has parametric equations x equals cos theta, y equals sine theta, and you know all that because that's just ordinary trigonometry. The hyperbola has parametric equations of x equals cosh t, or theta, whatever, and y equals sinh, like that. Just a little thought here. If you look in diagram A and you look at MP, which is in the same ratio as PN, MP to OM is in the same ratio as NP to OP. But if you look at MP, or MP0, it's a tangent. In diagram B, the same occurs, that for the point, for the line from M dash down to the axis is a tangent to the curve. It's kind of makes sense. This is an interesting thing. This is a bubble. If you look up catenoids, then you'll find why this is such an interesting thing and why it's relevant here. What it is, it's the, if you've got some soap, some bubble material, then the surface of this shape is what you get when you get a bubble that's gone across 2 rings rather than just one. It's very clever, very pretty. Just there, the diagrams to show you that the green one is e to the x, the red one is e to the negative x, and cosh is shown in green. Similarly, we've got the e to the x and we've got e to the negative x, and we've got sinh, and if you remember, sinh is half the difference of e to the x and e to the negative x, so that's just the definitional thing of it. Putting them all together in one place, you can see there e to the negative x divided by 2, e to the x divided by 2 in the left-hand diagram. Then you can see cosh and its relationship to sinh, and in the third diagram you can see tanch. This diagram has sinh, cosh and tanch all on the same diagram, so you can make a comparison. We can also graph the inverse functions by reflecting the curves in the line y equals x. This is the reference that I made before about a catenary. Suppose we've got a heavy chain that's drawn in the blue, and it's suspended at both ends and it hangs in the shape there, and the shape is defined as y equals a cosh x over b. When x is 0, y is equal to a cosh of 0, which then y is equal to a. When x is b, so this point here, then y is equal to a cosh of b over b, and b over b is 1, so a cosh 1 is, cosh 1, if you look it up on your calculator, is 1.54. So A is the point 0, A, and B is the point B 1.54. Now you don't need to know that, but it kind of sets the scene, and it's an engineering example of Kosh. We can just delete that. I'm not sure why that's in there, so delete that slide. But I don't know how to delete a single slide. We can also graph the hyperbolic version of cosecant, and similarly the hyperbolic secant. This one here is y equals hyperbolic cosecant, like that. This is the hyperbolic secant. And this is a graph of the hyperbolic cotangent.